Hello there, and welcome. Tonight we're going to leave the Earth behind. Not in any alarming way, not in any urgent or hurried way. We are simply going to let our minds drift outward, slowly and gently, the way starlight drifts across the dark, patient, unhurried, travelling impossibly far without any effort at all. The universe is very large. That is not a frightening fact. It is, in some deep and quiet way, a comforting one. Because when you are lying there in the dark and your thoughts are circling and your mind keeps returning to the same small worries, the universe reminds you softly, without judgment, that there is an extraordinary amount of space out there. Enough space for everything. Enough space, certainly, for all the things that were troubling you today to shrink down to something very, very small. Space has always done this for human beings, long before we had telescopes or satellites or any of the mathematics that let us understand even a fraction of what is actually out there. People lay on their backs in the dark and looked up and felt something ease in their chests. The ancients gave names to the stars not because they needed to, but because giving a name to something vast and distant makes it feel like company. And company in the dark is one of the oldest comforts there is. Tonight we are going to travel together through some of the most beautiful, most astonishing, most gently mysterious corners of deep space. We will visit nebulae that glow like stained glass windows in an empty cathedral. We will drift past stars so large that if one were placed where our sun sits, it would swallow every planet out to Jupiter without even noticing. We will spend time with the strange and quiet wonders of black holes, of dark matter, of light that has been travelling toward us since before the Earth existed. And through all of it, we will move slowly. There is no rush tonight. There is nowhere else to be. If you enjoy these gentle journeys, I invite you to like, subscribe, or leave a thought in the comments below. It helps others find their way here too, one sleepy soul at a time. For now, let your shoulders drop a little. Let your jaw unclench if it has tightened. Take one slow breath in and let it out even more slowly. You have nowhere to be. You have nothing to solve tonight. The universe has been here for nearly 14 billion years, and it will carry on perfectly well while you rest. Let's begin. The night sky, as most of us have seen it, is a modest thing. If you have lived most of your life in a city, the night sky might offer you 30 or 40 visible stars on a clear evening, a handful of bright points scattered across a dim, slightly orange expanse. You learn the obvious ones: Orion and his belt, the Big Dipper, Venus low in the west, so bright it barely seems to belong with the others. It is a pleasant sky, familiar sky, but it gives away very little of what is actually out there. Travel to a place without light pollution, a desert, a mountain plateau, the middle of a calm ocean, and the sky transforms into something almost incomprehensible. The familiar stars are still there, but now they are embedded in a river of faint, soft, overlapping light that stretches from one horizon to the other in a great tilted arch. That river is the Milky Way, and what you're seeing when you look at it is the collective light of somewhere between 200 billion and 400 billion stars, all of them belonging to our own galaxy, so numerous and so distant that their individual lights blur together into something that looks almost like cloud. That is the view from inside. We live inside the Milky Way, tucked in one of its spiral arms, about halfway between the centre and the outer edge. We can only ever see our galaxy from within, the way you might try to understand the shape of a vast building by walking around inside it, never able to step outside and take in the whole form at once. What we know about the Milky Way's shape, its elegant spiral arms, its central bulge, the long bar of stars that runs through its core, we know largely by observing other galaxies and reasoning backward. We look at their graceful pinwheel forms and say, yes, that is probably what ours looks like too. And our galaxy is, in the grand reckoning of the universe, a perfectly ordinary one. That thought deserves a moment. Our galaxy contains hundreds of billions of stars, each one a sun, many of them accompanied by their own systems of orbiting worlds. And our galaxy is ordinary. Not particularly large, not particularly small, not especially rich or especially sparse. When astronomers count galaxies in the observable universe, the number they arrive at is somewhere around 2 trillion. 2 trillion galaxies, each containing hundreds of billions of stars. There is a number beyond most human imaginations, and yet it is apparently just the accounting. What is remarkable is not that the universe is unimaginably large. What is remarkable is that despite its unimaginable largeness, it operates according to a set of rules so consistent, so elegant, so orderly that two scientists on opposite sides of the Earth, working completely independently, arrive at the same mathematics when they try to describe it. The universe is vast, but it is not chaotic, it is governed, and there is something deeply restful in that. Let us begin, as all good cosmic journeys do, close to home. Our sun is a star. This seems obvious, perhaps even unremarkable since we've grown up knowing it. But it is worth pausing to really feel the strangeness of it. The thing that warms your skin on a summer afternoon, the thing that turns the leaves gold in autumn and lifts the mist from the fields on a cold morning that is a star. A ball of nuclear fire about 1.5 million kilometers wide, sitting some 150 million kilometers away from where you are lying right now. The sun is classified by astronomers as a G-type main sequence star, which is their precise way of saying it is a medium-sized, middle-aged, yellow-white star of perfectly ordinary character. It has been burning for about 4.5 billion years. It will continue burning for roughly another 5 billion. In terms of stellar lifespans, it is in the comfortable middle of its existence past the energetic recklessness of youth, not yet approaching the dramatic changes of old age. What the sun actually is at its core is a kind of controlled catastrophe. Every second the sun converts about 600 million tons of hydrogen into helium through a process called nuclear fusion, and in doing so, it releases the energy that keeps our entire world alive. The sun does not burn the way a log in a fireplace burns. Combustion is far too tame a process to describe what happens inside a star. Instead, hydrogen atoms are pressed together so tightly under such extraordinary heat and pressure that they merge into helium, and in that merging they release a tiny amount of energy as described by Einstein's famous equation. That energy, carried outward through the body of the sun, takes somewhere between 10,000 and 100,000 years to travel from the core to the surface. Then it crosses the 150 million kilometers of space between the sun and the earth in just over 8 minutes. You can think of the sunlight warming your face as being, in some sense, incredibly old light energy that was locked in the sun's core since long before your grandparents were born, only now completing its journey. Our sun is one of the younger, more peripheral stars in the galaxy. The stars at the center of the Milky Way are generally older and were formed in a denser, more chaotic early universe. Many of those ancient stars are long since dead, having burned through their fuel and collapsed or expanded into beautiful ruin. The light we see from some of them left its source before the Earth existed. In a very real sense, when we look at distant stars, we're looking into the past. There is something else worth considering before we move outward into deeper space. Our solar system, the Sun and its 8 planets and their moons and the asteroid belt, and the distant icy bodies of the Kuiper belt and the great hypothetical shell of cometary material known as the Oort cloud. Our entire solar system, all of it, is a very small corner of a very ordinary galaxy. The distance from the Earth to the Moon is about 380,000 kilometers. The Apollo astronauts made that journey in roughly 3 days. The distance from the Earth to Mars, at its closest approach, is about 54 million kilometers, about 140 times farther than the Moon. The distance from the Earth to the Sun is about 150 million kilometers, and the distance from the Sun to the outer edge of our solar system, to the very edge of the Oort cloud where the Sun's influence finally fades into the broader fabric of the galaxy, is somewhere around 1 to 2 light years. A light year is the distance that light travels in 1 year, moving at roughly 300,000 kilometers per second. In terms of everyday units, a light year is about 9.5 trillion kilometers. So the outer boundary of our solar system sits somewhere between 9.5 and 19 trillion kilometers from the Sun, and the nearest star beyond our own, a small, dim red star called Proxima Centauri, part of a 3-star system called Alpha Centauri, is about 4.2 light years away. 4.2 times 9.5 trillion kilometers, even at the speed of the New Horizons spacecraft, which is the fastest object humans have ever launched from Earth. It would take about 70,000 years to reach Proxima Centauri. This is not a discouraging fact, though it might seem like one. It is simply an honest accounting of how genuinely enormous the distances involved in space travel really are. The universe did not build these distances to frustrate us. It built them because space is, after all, the fundamental medium of existence, and it is generous with it. Let us turn now towards something beautiful. The nebulae of deep space are, without question, among the most visually spectacular objects in the universe. A nebula, the word comes from the Latin for cloud or mist, is a vast region of gas and dust floating in space, sometimes spanning hundreds of light years across. They come in several varieties, each formed by different processes, each with its own character and colour and light. Some nebulae are the birthplaces of stars. These are called stellar nurseries, and they are regions where clouds of hydrogen gas and interstellar dust have begun, under the gentle but relentless tug of gravity, to collapse in on themselves. As the gas compresses and heats, points of density form seeds around which more gas gathers, and more, until eventually the temperature and pressure at the center become so extreme that nuclear fusion ignites. A star is born, and when a star ignites inside a nebula, the radiation it emits illuminates the surrounding gas, creating the glowing and dramatic clouds of color that make nebulae so visually striking. The most famous of these stellar nurseries is the Orion Nebula, which lies about 1,300 light-years from Earth, and is actually faintly visible to the naked eye. On a dark night, it is the fuzzy middle star in Orion's sword, though most people assume it is simply a dim star. Through even a modest telescope, it resolves into something astonishing, a great cloud of greenish and reddish light, tangled and layered and alive with structure, and embedded deep within it, a cluster of very young stars called the trapezium, still burning with the raw, brilliant heat of youth. Other nebulae are the remnants of dead stars, the beautiful wreckage left behind when a sun-like star reaches the end of its life and, instead of exploding, puffs up into a red giant and then gently expels its outer layers into space. These are called planetary nebulae, a misleading name given to them by early astronomers who thought their round shapes looked like planets through the telescope. They are not planets at all. They are stellar autumns, the slow, glorious dispersal of a star's outer body into the surrounding space, leaving behind at the centre only a tiny, incredibly dense remnant called a white dwarf. The Helix Nebula, sometimes called the Eye of God, is one of the closest and most studied planetary nebulae. It lies about 650 light-years from Earth and spans about 2.5 light-years across, meaning that if you placed it where our Sun is, its outer edge would extend roughly halfway to the next nearest star. Its colours, seen in long exposure photographs, are extraordinary. Concentric rings of blue and green and red and copper, the whole structure shimmering like a jewel left behind in the dark by something that no longer needs it. If your eyes are growing heavy now, that is perfectly fine. Let them close. The images we are describing will drift on around you, soft and slow, and the story will carry you where it wants to go. There is a type of nebula that speaks to something even more elemental than the birth or death of stars. When a massive star, one that is much larger than our Sun, perhaps 8 times as large or more, reaches the end of its life, the ending is not gentle. There is no slow puffing outward, no gradual dispersal of its outer layers. Instead, the star's core collapses in an instant, in less than a second, and the resulting shockwave tears the entire outer body of the star apart in an explosion so powerful that for a few days or weeks, a single star can outshine an entire galaxy of hundreds of billions of suns. This is a supernova. The light and energy released in a supernova is almost beyond any useful scale. But what is perhaps even more remarkable than the explosion itself is what it leaves behind. The shockwave from a supernova does not simply dissipate. It travels outward through the surrounding space at thousands of kilometers per second, compressing the gas and dust it encounters, heating it, illuminating it, and seeding it with the heavy elements carbon, oxygen, iron, nickel, gold that were forged in the star's interior during its lifetime and violently scattered in its death. The remnant of a supernova is called naturally a supernova remnant, and over hundreds or thousands of years it expands into a glowing shell of gas and debris that can span dozens or even hundreds of light years. The Crab Nebula, lying about 6,500 light years from Earth, is the remnant of a supernova that was observed by Chinese astronomers in the year 1054. They recorded it as a guest star, a new star that suddenly appeared in the sky, visible even in daylight for about 3 weeks. Today, nearly 1,000 years later, the material from that explosion is still expanding outward, still glowing, still evolving. At its centre sits a pulsar, the compressed remnant of the original star's core, now a sphere of neutrons only about 20 kilometers across, spinning 30 times per second and emitting pulses of radio waves with the regularity of the most precise clock ever built. The heavy elements scattered by supernovae do not simply float away into the void. They seed the gas clouds from which the next generation of stars forms. They become part of new stars, new planets, new moons, and they become, this is the part worth letting settle, part of us. The carbon in your body was forged in a stellar interior. The iron in your blood was forged in a supernova. You are, in the most literal chemical sense, made of stardust. That phrase has been repeated so often it has lost some of its power, but it is worth restoring it tonight. Every atom in your body, heavier than hydrogen and helium, was created inside a star that died long before our solar system existed. You are ancient, you are cosmic, and tonight you are resting. From here, the story shifts to something even more ancient, the universe itself in its infancy. The Big Bang, the name we give to the origin of the universe, did not actually occur as an explosion in space the way most of us picture it. There was no vast emptiness into which matter suddenly appeared and began expanding. Rather, the Big Bang was the beginning of space itself, the beginning of time itself, and everything in the universe. All the matter and energy that would eventually become stars and galaxies and planets and people was compressed into an unimaginably hot, dense state and then began to expand. This expansion has never stopped. It is happening right now. The universe is still growing, and every galaxy beyond our local group of galaxies is moving away from us. Not because galaxies are flying through space in every direction away from a central point, but because the space between them is itself expanding, the way dots drawn on a balloon move apart from each other when you inflate it. The more space there is between two galaxies, the faster they appear to recede from each other. Galaxies that are very far away are receding so quickly that the light they emit is stretched by the time it reaches us, its wavelength pulled along by the expanding space it has had to cross, shifting it toward the red end of the spectrum in a phenomenon called cosmological redshift. This redshift is how we know the universe is expanding, and by running the expansion backward in our minds by asking, if everything is moving apart now, where was it all before we arrive at the conclusion that, about 13.8 billion years ago, everything that now exists was once in a single point of infinite density? That moment was the beginning. What came before the Big Bang is a question that physics currently cannot answer. It is not that scientists are being evasive, it is that time itself, the very framework within which before has any meaning, appears to have begun at the Big Bang. Asking what happened before the Big Bang is a little like asking what lies north of the North Pole. The question is grammatically sensible but may not correspond to anything real. Some physicists propose that the universe cycles, that the Big Bang was preceded by a contraction, a big crunch of a previous universe. Others suggest that our universe is one of an almost infinite number of universes that have bubbled into existence from a larger multiverse. Others still are simply comfortable saying, we do not know. And in science, that is one of the most honest and respectful answers you can give to a question. There is something else worth considering, and it is one of the stranger and more beautiful mysteries in all of science. When astronomers look at the universe, when they measure how galaxies rotate, how light bends around massive objects, how the large-scale structure of the universe is organized, they find that the math does not add up. There is not enough visible matter to account for what they observe. Galaxies rotate in ways that would tear them apart if they contained only the stars and gas and dust we can see. Light bends more than it should around galaxy clusters. The overall structure of the universe, the vast cosmic web of filaments and voids, could not have formed the way it did from ordinary matter alone. The conclusion that cosmologists have arrived at reluctantly, carefully, through many decades of accumulating evidence is that most of the matter in the universe is invisible to us. It does not emit light. It does not absorb light. It interacts with ordinary matter only through gravity. And because we can detect it only through its gravitational effects, we call it dark matter. Dark matter appears to make up roughly 27% of the total content of the universe. Ordinary matter, everything you can see, touch, or measure directly, all the stars and planets and gas clouds and people and chairs, makes up only about 5%. The remaining 68% is something even stranger, something called dark energy, which appears to be driving the accelerating expansion of the universe. Dark matter pulls things together. Dark energy pushes things apart, and between them they account for 95% of everything that exists, while remaining, as of today, almost entirely mysterious. It is one of the most genuinely humbling discoveries in the history of science. All of our physics, all of our chemistry, all of our understanding of how the world works, everything built by thousands of years of human inquiry, all of it applies to 5% of what is out there. The rest, as yet, eludes us. And yet, even this does not feel threatening resting here in the dark. It feels instead like a reminder that the universe is not obligated to reveal everything at once. It is patient, and so can we be. There is nothing you need to hold on to right now. Let your shoulders drop a little if they have risen. Let your hands unclench, your face soften. You're in no hurry. Neither is this universe we're exploring together. Let us talk about stars for a while longer, because stars are among the most companionable things in the universe. A star at its most basic is a self-sustaining nuclear furnace, a globe of gas so massive that gravity compresses its interior until fusion begins, and so balanced in its tensions between gravity pulling inward and radiation pressure pushing outward that it achieves a kind of miraculous equilibrium and simply burns steadily for millions or billions of years without collapsing or exploding. Stars come in an enormous range of sizes, temperatures, and colours. The smallest stars, called red dwarfs, are dim and cool and red-orange in colour, and they burn so slowly that they can live for trillions of years, far longer than the current age of the universe. The most common stars in the galaxy are red dwarfs. If you imagine the galaxy as a city, red dwarfs are the steady, quiet neighbourhood homes that far outnumber all the grander buildings. Many of them are so faint that not a single red dwarf star is visible to the naked eye from Earth, even though the nearest star to our Sun is one. At the other end of the spectrum sit the massive stars, the blue supergiants and hypergiants, that burn so ferociously that they exhaust their fuel in only a few million years, a cosmic eye blink. These stars are rare but extraordinary. They are immensely hot. Their surface temperatures can reach 40 or 50,000 degrees Celsius, compared to our Sun's 5,500, and they blaze with a blue-white light that is almost unnervingly beautiful. They are the poets of the stellar world, brilliant, intense, and brief. One of the most celebrated massive stars in our galaxy is Eta Carinae, a system in the southern sky that contains at least one star, with a mass somewhere between 100 and 150 times that of our Sun. It is one of the most luminous star systems known in the Milky Way, and it is almost certainly going to explode as a supernova, perhaps also as a hypernova, at some point in the geologically near future. By geologically near, astronomers mean somewhere in the next 100,000 years or so. In terms of human lifespans, it could happen tomorrow, or it could happen long after the last human being has lived and gone. When it does explode, it will be visible from Earth in daylight, perhaps for weeks, and will be one of the most spectacular events our species has ever witnessed, if our species is still here to see it. There are also stars called variable stars, which do not shine with a constant brightness, but instead pulse or fluctuate in regular patterns. Some of these are intrinsically variable. Their brightness changes because the star itself is actually expanding and contracting in a slow rhythmic pulsation, like a slow breath. The most famous of these are called Cepheid variables, and they are one of the astronomers' most important tools for measuring distances across the universe, because the period of their pulsation is directly related to their intrinsic brightness. By measuring how fast a Cepheid pulses, and then comparing that to how bright it appears in the sky, you can calculate exactly how far away it is. These ordinary, patient, pulsing stars are the rulers with which we measure the cosmos. let us consider what it might feel like for a moment to stand on a world that orbits another star. We have known for only about 30 years that other stars have planets. Before the early 1990s, the existence of planets around other stars was assumed by many astronomers and dismissed by others, but there was simply no way to confirm it. The distances were too great, the planets too small and too dim, lost in the overwhelming glare of their parent stars. The first confirmed detection of a planet around another Sun-like star came in 1995, when astronomers Michel Mayor and Didier Queloz detected a planet orbiting a star called 51 Pegasi, about 50 light-years from Earth. They found it not by seeing it directly, but by detecting the tiny wobble it caused in its star. As the planet orbits, it exerts a small gravitational tug on the star, causing the star to move very slightly toward and away from Earth in a regular pattern that shows up in the star's light as a tiny but measurable change in wavelength. The planet was astonishing in ways that even the astronomers who found it did not expect. It was a gas giant, roughly half the mass of Jupiter, orbiting its star in just over 4 days, far closer than Mercury is to our Sun. No one had imagined a gas giant could exist so close to its star. The universe, as it so often does, had arranged things in a way that nobody predicted. Since that discovery, the floodgates have opened. The Kepler Space Telescope, launched in 2009, spent 9 years staring at a single patch of sky containing about 150,000 stars and watching for the tiny, regular dimming that occurs when a planet passes in front of its star and blocks a small portion of its light. Kepler found thousands of planets. Its successor missions have found thousands more. As of the early 2020s, astronomers have confirmed more than 5,000 exoplanets, worlds orbiting other stars, and there are thousands more candidates waiting to be confirmed. What emerges from all this data is a picture that is, in equal parts, humbling and wonderful. Planets are extraordinarily common. Most stars appear to have them. Many stars have multiple planets, and the range of planetary types is far broader than our own solar system suggested. There are hot Jupiter's gas giants roasting close to their stars, whipped to temperatures of thousands of degrees. There are super-Earth's worlds larger than our Earth, but probably rocky, possibly covered in deep oceans or swathed in thick atmospheres. There are mini-Neptunes, warm sub-Jovians, ice giants in distant orbits, most tantalizing of all rocky worlds in the habitable zones of their stars, where liquid water might exist on their surfaces. The question of whether any of these worlds harbours life is one of the most profound and unanswered questions in all of science. And for tonight, it can remain unanswered, lying open like a window to a starry night full of possibility, full of wonder, asking nothing of us but our quiet attention. Which brings us gently to a thought about water. Water is one of the most common molecules in the universe. This surprises many people who think of water as something specific to Earth, a special and fortunate condition of our particular world. In fact, water is a straightforward combination of two very common elements: hydrogen, the most abundant element in the universe, and oxygen, which is produced in stellar interiors and scattered through supernova explosions. Wherever hydrogen and oxygen meet, under the right conditions, water forms. Water has been detected in the atmospheres of gas giant exoplanets. It has been found in the form of ice in the cold outer reaches of our solar system. It exists in the giant molecular clouds of interstellar space. It has been found on the Moon, on Mars, on the moons of Jupiter and Saturn. Europa, a moon of Jupiter somewhat smaller than our own moon, is covered in a smooth crust of ice beneath which, most planetary scientists believe, lies a global ocean of liquid water kept liquid not by the warmth of the sun, which is far too distant, but by the tidal heating generated by Europa's gravitational interaction with Jupiter and its neighbouring moons. That ocean is estimated to be between 60 and 150 kilometres deep. It has been there, liquid and protected beneath the ice for perhaps billions of years. Whether anything lives in Europa's ocean, we do not know, but the conditioned liquid water, chemical energy from hydrothermal vents on the ocean floor, protection from the radiation of space by the ice above are not unlike the conditions in which life first emerged on Earth. The thought deserves to rest quietly in the mind without being pushed too hard in any direction. There might be life in the dark ocean beneath Europa's ice. There might not be. Either answer changes the way we think about the universe. Enceladus, a small moon of Saturn, is another world of extraordinary interest. It is tiny, only about 500 kilometers across, and yet from geysers near its south pole, it shoots plumes of water vapor and ice particles directly into space, where they spray outward into Saturn's rings and can be analyzed by passing spacecraft. The Cassini mission, which spent 13 years orbiting Saturn, flew directly through these plumes and detected water, salts, silica particles, hydrogen, and complex organic molecules. The presence of hydrogen is especially significant because it is a sign of hydrothermal reactions. Water interacting with warm rock on the seafloor, which is precisely the kind of chemical energy source that supports life in the deep ocean here on Earth. Enceladus is whispering something to us across hundreds of millions of kilometers, and we are still learning to hear it. Allow your breathing to find its own slow rhythm as we continue. You don't need to hold any of this tightly. Let it drift through your mind the way music drifts through a room, present but not demanding, beautiful but not urgent. These stories have been here for billions of years, and they'll be here long after tonight. Let us talk now about the strange, patient, almost philosophical nature of light. Light is the thing that connects us to the universe. Everything we know about what is out there, every star, every galaxy, every nebula, every exoplanet we know because of light that has travelled across space and arrived at our telescopes, our eyes, our instruments. We cannot reach out and touch the stars. We cannot send a probe to a galaxy 20 million light years away and wait for it to radio back its findings. All we have is light. And light, it turns out, is both a wave and a particle. This is one of the stranger findings of 20th century physics, and it remains genuinely strange not because physicists don't understand it mathematically, but because it does not have any comfortable everyday analogy. A wave is a continuous spread-out disturbance. A particle is a discrete localized object. Light is both, simultaneously, depending on how you try to observe it. A photon of light, a single particle of light, can be produced by an electron in an atom dropping from a higher energy level to a lower one. The energy difference is released as a photon with a specific wavelength, and that wavelength determines the color of the light. Red light has a longer wavelength than blue light. Ultraviolet light has a shorter wavelength than violet. Beyond both ends of the visible spectrum, which represents only a tiny sliver of the full electromagnetic spectrum, are wavelengths that our eyes cannot detect at all. Radio waves, microwaves, infrared, ultraviolet, X-rays, gamma rays. All of these are forms of light, differing only in their wavelength and the energy they carry. One of the most beautiful facts about light is what happens when you spread it out through a prism or a diffraction grating. The white light of a star passed through such a device spreads into a rainbow, and within that rainbow at specific and precise wavelengths, you will find dark lines, gaps where particular wavelengths are absent. These dark lines are the fingerprints of atoms. Every element absorbs and emits light only at its own characteristic wavelengths, like a private code. By reading the pattern of dark lines in a star's spectrum, astronomers can determine exactly what elements that star contains, how hot it is, how fast it is rotating, and whether it is moving toward or away from us. All of this from a streak of light barely wide enough to see. This technique, called spectroscopy, allowed astronomers to discover helium in the Sun before they had ever detected it on Earth. The element was found in the solar spectrum in 1868 and named after Helios, the Greek god of the sun. When chemists eventually found helium in natural gas wells on Earth in 1895, they recognized it because its spectroscopic signature matched. The sun told us about helium before the ground did. Stars are born in pairs, more often than not. Single stars like our sun are actually the exception rather than the rule. The majority of star systems in the galaxy are binary or multiple 2, 3, sometimes even 7 or 8 stars orbiting each other in complex, interlocking gravitational dances. In a binary system, 2 stars orbit their common center of mass, the way 2 children of different sizes balance on a seesaw at different distances from the center. Binary stars can be very different from each other, or very similar. Some binaries are so close together that they nearly touch, orbiting each other in hours. Others are so far apart that they take thousands of years to complete a single orbit. Some binary systems contain stars of very similar mass and brightness. Others pair a brilliant blue giant with a small dim red dwarf, an odd couple by any measure, travelling together through the galaxy without any apparent awareness of how different they are. Some binary stars, over time, interact in ways that produce spectacular phenomena. If one star in a binary is a red giant, a star that has expanded enormously in the late stages of its life, and the other is a compact remnant like a white dwarf. The white dwarf can pull hydrogen off the surface of its giant companion, accumulating that hydrogen on its own surface over thousands of years until the accumulated layer becomes hot and dense enough to ignite in a thermonuclear flash. This produces an event called a nova, a sudden dramatic brightening of the star system, visible from Earth as a new star appearing in the sky, where before there seemed to be nothing. After the flash subsides, the white dwarf remains and the process begins again. Some novae occur every few decades or so. There is something almost meditative about this cycle. The patient accumulation of hydrogen, the sudden release, the quiet settling back. The accumulation beginning again. It has happened millions of times in the galaxy. It will happen millions more, and watching a nova from Earth, seeing a small point of light brighten and fade over weeks or months, is to watch a process that has played out in its unhurried rhythm for billions of years. Let us move on now to something that is perhaps the most dramatic object in the entire universe: black holes. The name carries a dramatic weight in popular culture that the actual objects, in a certain sense, exceed. A black hole is a region of space where the gravitational field is so strong that nothing, not matter, not radiation, not light itself can escape. The boundary of this region is called the event horizon, and it is not a physical surface. There is no wall at the edge of a black hole, no surface to touch or crash into. The event horizon is simply the mathematical boundary beyond which the escape velocity, the speed you would need to travel to break free of the black hole's gravity exceeds the speed of light. Since nothing can travel faster than light, and since the speed of light is the universal speed limit, anything that crosses the event horizon is committed to an inward journey with no return. This was predicted by Einstein's general theory of relativity, published in 1915, as a mathematical possibility and extreme solution to the equations. For decades, physicists debated whether black holes could actually exist in nature, or whether they were merely a mathematical curiosity. We now know that they exist, and that they exist in great numbers. Black holes form in several ways. When a massive star dies in a supernova, its core collapses, and if the core's mass is above a certain threshold, no known force can halt the collapse, not electron pressure, not neutron pressure, not any other repulsive force. The core collapses indefinitely, all of its mass concentrating into a single point of infinite density called a singularity, surrounded by the event horizon. This is a stellar mass black hole, typically containing between 5 and a few tens of times the mass of our Sun. But there is another category of black hole that is stranger, and in many ways more fascinating, the supermassive black hole. These are the giants that lurk at the centres of galaxies, and they contain not a few times the mass of a star, but millions or billions of times the mass of a star. The supermassive black hole at the centre of our own Milky Way galaxy, called Sagittarius, a star, contains about 4 million times the mass of our Sun. The supermassive black hole at the centre of the galaxy Messier 87, which famously became the first black hole ever directly imaged in 2019, contains about 6.5 billion solar masses. The image of Messier 87's black hole, produced by the Event Horizon Telescope collaboration, a network of radio telescopes around the world functioning together as a single Earth-sized instrument, showed a fuzzy orange ring of hot, glowing gas surrounding a dark central region. It was exactly what Einstein's equations predicted it would look like over a century after those equations were written. The equations had been holding that prediction patiently for 100 years, and the observation confirmed them in the most direct way possible. There is something genuinely peaceful about contemplating black holes from this safe and comfortable distance. The popular imagination of a black hole is something menacing, a cosmic drain, a destroyer, something that devours and destroys. But from a slightly different perspective, a black hole is simply the universe's most thorough expression of gravity. It is matter compressing itself as far as it possibly can, pulling the fabric of space inward with extraordinary patience. Black holes do not reach out and grab things from a distance. They simply sit there, and if something comes within their event horizon, it stays. They are not hunters. They are more like deep pools in a landscape. If you don't wander too close, you are in no danger. What happens inside a black hole is one of the most genuinely unknown questions in physics. The singularity at a black hole's center is a point where the equations break down, where they produce infinities that physicists understand, to be a sign that the theory needs to be extended or replaced, not that infinities actually exist. Many physicists believe that a complete theory of quantum gravity, which does not yet exist, would resolve what actually happens at the center of a black hole and replace the singularity with something more physically meaningful. We are still waiting for that theory. What we do know is that from a great distance, a black hole is almost serenely ordinary. It exerts gravity like any other massive object. It can orbit and be orbited. It can be part of a binary system. The only unusual thing about it from far away is what it doesn't do. It doesn't shine. It sits in the dark, enormous and quiet, and the universe goes about its business around it. Let us drift now, away from individual objects and towards something larger, the architecture of the universe itself. When astronomers look at the largest scales, what they see is not a uniform, featureless distribution of galaxies spread smoothly through space. What they see is structure an intricate three-dimensional web of filaments and clusters and voids that cosmologists call the cosmic web. Galaxies do not sit in isolation. They collect into groups, groups collect into clusters, clusters collect into superclusters, and the superclusters themselves are arranged along long, curving filaments of dark matter and ordinary matter, like pearls strung along threads, separated by enormous empty voids hundreds of millions of light-years across. A Milky Way belongs to a small group of galaxies called the local group, which includes our galaxy, the Andromeda Galaxy, the large and small Magellanic Clouds, and several dozen smaller dwarf galaxies. The local group spans about 10 million light-years. It is, in the cosmic web, a very modest neighbourhood. The local group itself is part of a larger structure called the Virgo supercluster, also known as the local supercluster, which contains hundreds of galaxy groups and clusters spread across a region about 110 million light-years across. And the Virgo supercluster is itself just one lobe of an even larger structure called the Laniakea supercluster, a name drawn from Hawaiian that means immeasurable heaven. Laniakea contains about 100,000 galaxies and spans roughly 500 million light-years. The Milky Way sits near the edge of one of Laniakea's outer arms, slowly being drawn, along with the rest of the local group, toward a massive gravitational centre called the Great Attractor, a region of concentrated matter so dense that it draws galaxies toward it across hundreds of millions of light-years. And Laniakea itself is just one supercluster in the observable universe, which contains approximately 10 million such superclusters. The observable universe, just the portion of it that we can in principle see, limited by how far light has had time to travel since the Big Bang, is about 93 billion light-years across. It is not the entire universe. It is simply the part we have access to, the bubble of space-time within which any light emitted has had time to reach us. The full universe, if it has an edge at all, is almost certainly much larger. If your thoughts are beginning to soften around the edges, that is exactly as it should be. There is nothing here requiring your attention, nothing to remember, just the quiet, enormous fact of space, drifting on around you, vast and patient and entirely indifferent to whether your laundry is done or your inbox is full. Let those thoughts go. They will wait for morning. Let us turn now to something quieter, and perhaps stranger. The universe is full of radio waves. Almost everything in space emits some form of electromagnetic radiation, and a great deal of that radiation falls in the radio part of the spectrum wavelengths, far too long for the human eye to see, stretching from millimeters to meters to kilometers. Pulsars emit radio waves, quasars emit radio waves. The hot gas swirling around supermassive black holes emits radio waves. The cosmic microwave background radiation, a faint uniform glow of microwaves that fills all of space and represents the cooled remnant of the Big Bang's fireball, fills the universe with a whisper of radio noise in every direction. Radio astronomy has opened an entire dimension of the universe that is invisible to the eye. The first radio telescope was built in 1937, and since then radio telescopes have discovered quasars, pulsars, the cosmic microwave background, and enormous clouds of hydrogen gas in the disks of galaxies, among many other things. The dish of the Arecibo Observatory in Puerto Rico, 305 meters across, and for decades the largest radio telescope on Earth, sat inside a naturally formed limestone sinkhole and gazed steadily at the sky for more than 50 years. When it collapsed in 2020, astronomers around the world mourned it as a friend. One of the most intriguing and still unresolved phenomena in radio astronomy is something called fast radio bursts. These are brief, intense flashes of radio waves lasting only milliseconds that appear to originate from sources billions of light years away. The energy released in a single fast radio burst in those few milliseconds is equivalent to what our sun produces in 3 days. For a time after their discovery in 2007, their origin was completely unknown, and some speculative voices suggested carefully, and without much expectation of being taken seriously, that they might be evidence of highly advanced technological civilizations using powerful transmitters for purposes we could not guess. The current scientific consensus is more pedestrian but no less remarkable. Fast radio bursts appear to come from magnetars, a type of neutron star with an extraordinarily powerful magnetic field, capable of releasing enormous amounts of energy in sudden bursts as their magnetic fields shift and crack. Some fast radio bursts repeat, which has allowed astronomers to study them more closely and gather clues about their nature. Others appear to flash once and never repeat. The mystery is not yet fully solved, but it is well on its way to being understood, and the answer, when it comes, will tell us something new and interesting about the behavior of matter under extremes of gravity and magnetism that nothing on Earth can reproduce. The universe speaks to us in many languages, not just radio waves. In 1915, Einstein's general relativity predicted another form of cosmic communication, gravitational waves. These are ripples in the fabric of space-time itself, produced when massive objects accelerate and particularly when two very massive compact objects, like neutron stars or black holes, spiral toward each other and merge. As they spiral inward, they produce gravitational waves that radiate outward through space at the speed of light, stretching and squeezing everything they pass through. For 100 years, gravitational waves were purely theoretical. The stretching and squeezing produced by any source distant enough to be of interest was so tiny a fraction of the diameter of a proton that no instrument seemed capable of detecting it. And then, in the early 21st century, two instruments called LIGO, the Laser Interferometer Gravitational Wave Observatory, with facilities in Louisiana and Washington state, were refined to a sensitivity that no one had previously imagined achievable. On September 14, 2015, LIGO detected a signal, a chirp. Scientists called it a rapid rise in frequency over a fraction of a second. The signal was consistent with the merger of two black holes about 36 and 29 times the mass of the Sun, about 1.3 billion light-years away. In the final moments of their merger, the two black holes radiated more energy in gravitational waves than all the stars in the observable universe emit in light during the same period. And the instrument on Earth detected the distortion this produced in space, a distortion smaller than 1,000th the diameter of an atomic nucleus. It was announced in February 2016, and the announcement produced an emotion among scientists and science enthusiasts that felt very much like awe. Since then, dozens more gravitational wave events have been detected, including the merger of two neutron stars, an event that was also detected in light across the electromagnetic spectrum, opening a new era of what astronomers call multi-messenger astronomy. We are now listening to the universe not only with light but with gravity itself. After billions of years of sending signals, the universe has found a new way to reach us. There is something else worth considering, and it is one of the most quietly extraordinary facts I know. The universe is transparent. This was not always the case. In the very early universe, for the first few 100,000 years after the Big Bang, the universe was so hot and dense that light could not travel freely. Photons were constantly being absorbed and re-emitted by the dense soup of charged particles that filled space. The universe was opaque, like a very dense fog. No light from that era could travel freely, and so we have no direct visual record of it. Then, about 380,000 years after the Big Bang, the universe had cooled enough that electrons could settle into orbit around atomic nuclei. When this happened, the sea of charged particles that had been trapping light disappeared, and suddenly on cosmic timescales, almost instantaneously the universe became transparent. Light was free to travel, and the light that was released at that moment, streaming outward in all directions from a universe that was suddenly no longer opaque, is still travelling through space today, 13.5 billion years later. It is the cosmic microwave background radiation, and it fills the sky in every direction with a faint glow of microwaves, a fossil of light from the universe's own infancy. When you look at a night sky full of stars, you're seeing light that has travelled for years or thousands of years or millions of years to reach you. But the cosmic microwave background radiation is light that has been travelling for over 13 billion years. It is, in a certain sense, the oldest light it is possible to see, the last light of a universe just becoming itself, arriving here tonight without any urgency after an unimaginable journey. Let us talk now about neutron stars, which are among the most extreme objects in the universe. When a massive star exhausts its fuel and explodes as a supernova, it sometimes leaves behind not a black hole but a neutron star, a remnant so compressed that a single teaspoon of its material would weigh approximately 1 billion tons. Neutron stars are typically about 20 kilometers in diameter, roughly the size of a small city, but they contain between 1.5 and 2 or more times the mass of our Sun. They're so dense that the protons and electrons in their cores have been crushed together to form neutrons, hence the name, and the matter inside them exists in states that physicists are still working to understand. Neutron stars have surface gravity about 200 billion times stronger than Earth's. If you could stand on the surface of a neutron star, which you obviously could not, for many reasons, your weight would be about 14 trillion times what it is now. You would be, in the briefest possible moment, a very thin smear of matter. What neutron stars do is rotate. All stars rotate, but when a star collapses from something many times larger than our Sun to something 20 kilometers across, the rotation speeds up enormously, for the same reason that a spinning figure skater spins faster when they pull in their arms. Some neutron stars rotate hundreds of times per second. These are the pulsars neutron stars that emit beams of radio waves from their magnetic poles, and whose rapid rotation sweeps those beams around like the beam of the lighthouse. Every time the beam sweeps past Earth, our telescopes see a pulse of radio waves, regular as clockwork. The first pulsar was discovered in 1967 by astronomer Jocelyn Bell Burnell, and she and her supervisor very briefly called the signal LGM1, standing for Little Green Men, before concluding that the regularity of the signal had a natural, non-artificial explanation. It is one of science's more charming almost moments. Neutron stars can also be magnetars, a variety of neutron star with magnetic fields trillions of times stronger than Earth's. Magnetars occasionally release enormous bursts of gamma rays and X-rays in what are called starquakes, sudden shifts in the rigid crystalline crust of the neutron star as the intense magnetic field restructures. In 2004, a magnetar located about 50,000 light-years away in the Milky Way released a burst of energy so intense that it measurably affected the ionosphere of Earth, even though it was 50,000 light-years distant. In astronomical terms, that is practically next door, but even so, the burst had crossed that unimaginable distance and still left a detectable mark on our planet's upper atmosphere. It reminds us that the universe is connected, even across distances that seem beyond any connection. From here, the story shifts to something more intimate, the question of what happens when a galaxy grows old. Galaxies are not static. They evolve. They grow by accreting gas from their surroundings, by merging with smaller galaxies, by consuming dwarf galaxies in gravitational interactions. They also change internally as their stellar populations age. The massive, short-lived blue stars die off, and the long-lived red and yellow stars come to dominate, giving an aging galaxy a warmer, redder hue. Our own Milky Way is currently in what astronomers consider its mature phase, actively forming new stars at a modest rate, a few stars per year, fueled by the gas that continues to drift in from its surroundings. But at some point that gas supply will run low. The raw material for new stars will be exhausted or expelled. The galaxy will gradually stop making new stars, and the existing stars will age and die without replacement. Over many billions of years, the Milky Way will turn red and dim, and eventually what's left will be a vast, cold collection of stellar remnants, white dwarfs, neutron stars, black holes, and perhaps cold, dark, burned-out hulks that were once stars floating quietly through a vast and slowly emptying space. This process is called quenching. It has already happened to many galaxies in the universe, particularly the large elliptical galaxies that sit at the centers of galaxy clusters, where the gas supply was consumed or expelled long ago and star formation has long since ceased. These dead or dying galaxies, glowing only with the ancient red light of their oldest stars, are sometimes called red and dead galaxies, and they are in a sense the universe's way of showing us that even the most extraordinary things have their natural lifespans. But even quenching takes billions of years, and the universe is still young enough that most galaxies are still very much alive and active. We are nowhere near the cosmic dusk. We are, if anything, in the afternoon. It is worth pausing here for a moment. We have travelled a great distance tonight, even without moving. We have visited stellar nurseries where clouds of gas become suns. We have stood near the quiet gravity wells of black holes. We have listened to the radio voices of magnetars and pulsars. We have watched galaxies evolve and age, and we have held in our minds, however loosely, the strange and beautiful fact that the universe is made mostly of things we cannot yet see or understand. These are not frightening thoughts. They are freeing ones. The universe is enormous and old and complex, and will carry on long after all of this, long after you and I and everyone we know, and everyone who has ever lived. And somehow, inside all of that enormity, the particular arrangement of atoms that makes up a person who is tired and lying in the dark and trying to sleep, that too is part of it. You're not outside the universe looking in. You're a piece of it, temporarily assembled, and right now that piece is doing exactly what it needs to do. Let your eyes be heavy. Let your thoughts slow and soften. There is nothing more required of you tonight. Let us continue gently. The Andromeda Galaxy is the most distant object visible to the naked eye from Earth. It lies about 2.5 million light-years away, and in a dark sky, it appears as a faint oval smear of light, slightly larger than the full moon. It is the nearest large galaxy to our own, and it is also, in the cosmically patient timescale of galaxy interactions, our galaxy's approaching companion. Andromeda and the Milky Way are moving toward each other. They have been for billions of years. Astronomers calculate that in about 4.5 billion years roughly, as long as the Earth has existed, the two galaxies will begin to collide. The collision will take several billion more years to complete, as the two galaxies pass through each other, interact gravitationally, and gradually merge into a single larger elliptical galaxy. Some astronomers have taken to calling this future merged galaxy Milkomeda, a name that has a certain endearing ungainliness to it. The collision sounds catastrophic, but it almost certainly won't feel that way to anything existing on planets within it. The stars in both galaxies are so far apart that the probability of any two stars actually colliding is vanishingly small. What will happen is that the gravitational interaction will disrupt the orbits of stars and the structure of both galaxies, sending some stars spiraling inward and others being flung outward into deep intergalactic space. The night sky, for an observer on a hypothetical planet in either galaxy, would transform over millions of years, familiar constellations slowly shifting, the neighbouring galaxy growing larger and more dramatic in the sky, vast tidal streams of stars trailing off in great arcs across the heavens. Our Sun and its planets may or may not survive the merger intact. Most likely the solar system will be displaced to a different region of the merged galaxy, but will continue to orbit the new galactic centre without great disruption. The Earth, if it still exists, will likely still be there. It will simply be part of a new, larger, quieter galaxy. Now let us consider something that orbits much closer to home. Our moon is extraordinary. The moon is the only celestial body beyond Earth that human beings have visited. 12 people have walked on its surface, all during the Apollo program between 1969 and 1972, and since the last of them lifted off in December 1972, no human being has been more than a few hundred kilometers from Earth's surface. The moon has sat there, waiting, for more than 50 years. The moon is about a quarter of the Earth's diameter, making it unusually large relative to its parent planet. Most planetary moons are tiny compared to their host worlds. Our moon is not. It is large enough to have a significant gravitational effect on Earth, raising the ocean tides, stabilizing the tilt of Earth's axis, and slowing Earth's rotation over geological time through tidal friction. Without the moon, Earth's axial tilt, currently about 23.5 degrees, producing our seasons would vary chaotically over millions of years, causing climate swings that might have made complex life difficult to sustain. The leading theory for how the moon formed is called the giant impact hypothesis. About 4.5 billion years ago, when the solar system was young and still busy assembling itself, a body roughly the size of Mars, a protoplanet that scientists call Theia, struck the young Earth in a glancing collision. The impact vaporized the outer layers of both bodies, ejecting an enormous cloud of molten rock and vapor into orbit around Earth. Over time, this cloud coalesced under gravity into the moon we know today. The moon was initially much closer to Earth and has been slowly spiraling outward ever since, currently moving away from us at about 3.8 centimeters per year, roughly the rate at which your fingernails grow. The moon's surface, frozen in its ancient appearance by the absence of weather or geological activity, is covered in craters from billions of years of meteorite impacts, as well as the smooth, dark plains called Maria Latin for seas, which the early astronomers named when they thought they might actually be bodies of water. They're instead vast fields of ancient solidified lava, produced by volcanic activity billions of years ago when the moon's interior was still warm and active. One of the quieter beauties of the moon is its light. Moonlight is, of course, reflected sunlight. The moon has no light of its own, but shines because its surface catches and scatters the sun's rays. On a clear night with a full moon, the light is bright enough to cast shadows, to read by, to walk safely through a dark forest. For most of human history, the full moon was the only reliable nighttime illumination available to people, and entire calendars, agricultural, religious, navigational, were built around its phases. The word month itself is rooted in the word moon, as is the word Monday, which was once Moon's Day. To lie on a clear night and see the moon is to see the same object that every human being who has ever lived has also seen. Every war and every love letter and every meal cooked and every child born, all of it happened under the same moon, the same patient, slowly retreating companion, shining its borrowed light down with complete impartiality. Let us travel outward again, past the moon, past the planets, past even the outermost reaches of our solar system. The space between the stars is not empty. It is filled with what astronomers call the interstellar medium, a thin but vast expanse of gas, mostly hydrogen and dust, and the occasional molecule, and the magnetic fields that thread through the galaxy and cosmic rays, the high-energy particles, mostly protons, that streak through space at nearly the speed of light, produced in supernova explosions in the environments around black holes. The interstellar medium is extraordinarily thin by any earthly standard. The best vacuum we can produce in a laboratory is denser than the interstellar medium, and yet, because space is so vast, the total amount of gas and dust in the interstellar medium is enormous. It makes up about 10 to 15% of the total mass of the Milky Way's disk. Within the interstellar medium, astronomers have identified something remarkable: complex molecules. Not just simple molecules like hydrogen or carbon monoxide, but genuinely complicated ones. Water, formaldehyde, ammonia, methanol, ethanol. Yes, ethanol. The same compound as in wine and beer, floating through the interstellar medium, and even more complex molecules involving dozens of atoms arranged in rings and chains. These complex organic molecules are the chemical precursors to life as we know it, and they exist throughout the galaxy, produced in the gas clouds around dying stars and floating through space until they are incorporated into a new solar system, a new planet, where they may serve as the raw material for something more. The discovery of complex organic molecules in space is one of the reasons many scientists believe that life, if it exists elsewhere, is likely to have access to the same basic chemical toolkit that life on Earth used. The universe appears to be generous with its chemistry. There is one more category of object I want to visit with you tonight, because it is perhaps the most quietly astonishing thing in all of astronomy. A quasar, the name shortened from quasi-stellar radio source, a relic of the early confusion about what these things were, is the most luminous, persistent object in the universe. A quasar outshines its host galaxy by factors of hundreds or even thousands. The brightest quasars emit more light than 1 trillion suns. They are visible across distances of billions of light years, which means that when we observe them, We are seeing objects as they existed billions of years ago in the young universe. What a quasar actually is at its heart is a supermassive black hole in the process of actively consuming an enormous amount of material. As gas and dust falls toward the black hole from a surrounding disk of material called the accretion disk, it compresses and heats to millions of degrees, releasing vast amounts of energy as light across the entire electromagnetic spectrum. The black hole itself does not emit this light. The light comes from the superhot material in the disk before it crosses the event horizon. It is the universe's most spectacular drain, glowing with an almost inconceivable brightness before the material disappears forever. You've been here long enough tonight. You can go now. Sleep well, and good night.